channel Northstar Continuous Knowledge Excellence. My name is Karuna Singh. In this video, we will get to know about the consequence of size reduction and why small systems are more reactive. So now our expert Professor Himadri B. Bohidar, who is associated with National Center in Agro-Nanotechnology, Terry Diker Nanotechnology Center, India. He has 31 years of academic experience in teaching and research. His area of expertise includes nanoscience and nanotechnology, nanobiointerface science, soft matter science, polymer physics, biophysics. We'll explain you in detail about this topic. So to get complete information, watch full video without skip.
Now, I just told you that as a size reduces, the material properties change. This is a very classic example of that in an experiment that has been conducted to prove this statement. Let me start from this beginning, topmost slide here. This is typical human hair, how it looks like. It has a thickness about a couple of microns. Now suppose I take a 60 micron diameter particle, comparable to the size of human hair thickness. Now, this is somehow smashed into 1 million particles. That each particle will have a diameter of about 600 nanometer. Now I further break it down, this fraction, to 1 billion particles of 60 nanometer. So we have 60 microns here, 600 nanometers, then again down to 60 nanometers. Then we have 1 billion small, tiny particles, nanoparticles here. What have we achieved by doing this? What we have achieved is we have increased the surface area of the material. The total surface area of this material is much less than this, and this is much less than this one. The available surface area, as it increases, the reactivity of the particle increases. Second thing, you realize that as the particles become smaller and smaller, there are fewer atoms in the particle. If you have fewer atoms in the particle, in a stable structure, the atoms are bonded to each other through various interactions, mostly covalent bonds and many other structures. And these keep the material stable. So as you break it into smaller and smaller size, lots of these bonds have to be broken to achieve this small size. When you break all these bonds, there are a lot of free electrons that are generated in the process. They will come immediately and sit on the surface of these nanoparticles. So the available free electrons on the surface of this one is much less than this one, and what is available here is much, much more than what is available here. More free electrons means more reactivity. The material will become highly, highly reactive because electrons can be exchanged very easily. Okay, now look at this plot here. Here there is a melting temperature, y-axis. X-axis is the size of a nanoparticle. There's a gold nanoparticle diameter shown here. When it is 1000 nanometer, which is the bulk gold instance, for instance, not a nanoparticle. It is more than 100 nanometers, it's not gold. Okay, it's not a nanomaterial. This is a bulk gold. The melting temperature is something like 1380, close to that, Kelvins. Reduce the size here. As its size falls, you can see that at 100 nanometer typically, it starts deviating from this plateau value and starts reducing. And at a value of something like 2 to 3 nanometer here, melting temperature has become close to 1000 Kelvins. So we have reduced it from 1400 to close to about 1000 or less than 1000 Kelvins here. This is happening because now much less energy is required to melt it because many of these bonds are already broken compared to here where all the bonds were alive and they are existing.
Wait. Are you worried about your project, training, dissertation, internship? Don't think too much because Nanoscience and Technology Consortium, in short NSTC, is giving you a golden opportunity to do the same tasks. NSTC also conducts workshops on amazing topics So if you want to register in the workshop, the registration link is given in the description box below, or you may go to the website www.nanoschool.in, where you can easily enroll in the workshops. So just check it out right now.
By reduction of the size, many of these bonds have been removed already. So there is no energy need requirement to kill those bonds or remove those bonds. Therefore, one is able to melt it at a much lower temperature. And therefore, the melting temperature will drop. And this is the typical proof which says that 100 nanometer is this nanometer threshold size. It should be less than that, because you can see at 100, the value of the melting temperature starts to fall drastically like this. And it all happens at 100 nanometer. Above that, it's all flat, nothing happens. It's bulk gold. Here, nano gold. Now, telling the story in a different language, you have, suppose, 16 spheres here. I have kept them touching each other to make a configuration, compact configuration. If you make a configuration like this, then you just count. This is an illustrative example to tell you what happens when the size reduces. There are 5 sitting inside the core, 1, 2, 3, 4, and 5. This 5. And rest are on the surface. 11 are on the surface. So if you find out how many of them are on the surface by how many there are in the core, the ratio, the surface to core ratio is 2.2 here. This is bulk material. Reduce the size to half, 8. Then you see, then there is only 1 inside the core. Rest are all on the surface. So surface to core, this has become 7. There are more, 3 times more than this on the surface. By reducing the size by half, we have increased the number of surface by 3 times. Now we just remove the 1 to next half, and then we have 4 of the spheres there. And then if these 4, all of them are on the surface. There is nothing at the core. So the contribution of the core becomes 0 here. Because everything is on the surface, 4 on the surface. So 4 over 0, the ratio becomes infinity. Means all these 4 atoms, if you think of, will be reactive, and they will react very strongly with the neighboring or available reactive sites. Okay, so more atoms on the surface means more electron availability on the surface, and more free electron availability on the surface means more reactive the material is. Okay, if you also look at the periodic table, you'll find that the elements that have more electrons that are freely available, free electrons, they are more reactive than systems or the elements which have fewer free electrons. The same philosophy works here. Now, when it comes to synthesis of these nanomaterials, there are 2 ways of synthesizing this. One is you take the bulk and just smash it down to smaller and smaller size mechanically. By applying physical force, you break it down to smaller and smaller size. And ultimately, you get less than 100 nanometer particle. That is possible. You can do it mechanically. Second approach is you start from the molecule level, and then you synthesize it through a chemical reaction. And then you end up with the stable clusters, nanoclusters, and they end up with a nanoparticle size of dimension typically of the order of 100 nanometer. And there is another way of doing the same thing. Target is here, either we come from this or we go from this method. Both the processes have their own advantages and disadvantages, and the point of caution here is not everything can be smashed down to this state. Whereas many of these nanomaterials can be synthesized in the bottom-up approach. And here we have much more control over the synthesis process, because we are starting from the basic building block, the atomic level. Then we know how to control the reaction. We know where to stop it. We can keep real-time monitoring of the growth process of the nanomaterial. Therefore, arriving here is much more structured and much more organized. But if you want to create materials in bulk, this is the cheapest way. bulk production, but poor quality of nanomaterial. This is reduced production, but extremely high quality of nanomaterial. So for most high sensitive work where you need more finesse, more efficiency, more output or more catalytic activity of the material, it is advisable to go from the bottom-up approach and follow the synthesis process from the atomic scale. Okay, this is an illustration of how the bottoms-up approach work. You just take the basic element and then assemble it together to create a superstructure. That's what it is.
I hope you liked this video. Here, I would like to give you an important information that Nanoscience and Technology Consortium organize the nanotechnology workshops on amazing topics. Also, I would like to tell you about the initiatives of NSTC in which you can also be a part of. The very first one is mentorship, second, patent commercialization, third, joint product development, fourth, research projects, fifth, consultancy services, sixth, nanomaterials for your research projects, seventh, training programs or customized training programs, eighth, workshops or customized workshops. So that's all. If you want to see these type of videos, then please do comment. We will definitely reach out to you. Subscribe to the channel Knowledge Star and hit the bell icon to never ever miss an update. Thank you.
For more updates, subscribe to our channel, click the links shown on the screen to stay connected.